In Chapter 23 on electric potential, we found that the differential work is equal to moving the charge through a potential and having a differential charge moving through a potential gave us our differential work. So if we want to find the total amount of work, then that's going to be equal to the integral from 0 to some q, our total charge that we want to move, v dq. But we know that q is equal to c times v, so v is just equal to q over c. So we can put that into our formula here. And let's make this a small q so we don't get our q's mixed up. Okay, now the 1 over c can come out. We have an integral from 0 to q of little q d little q. And the integral is just equal to little q squared over 2 from 0 to q. And that just gives us q squared over 2 times c. So this is the total amount of work required to put some charge q on a capacitor. Now the potential is going to equal 1/2 q squared over c. But if I put my relationship in for charge, I can find that I have 1/2 c v squared. And if I put in my relationship for c, then I'm going to get 1/2 charge times potential. And if I put my parameters in for the dimensions of a parallel plate, I get 1/2 epsilon naught the E field squared times A times D. Now this quantity AD is called the electric field density volume, because the area times the distance is a volume, and you have the electric field in that space. It's actually electric field squared. So all these formulas can be used to calculate the work to put the charge onto the capacitor and the amount of potential work available to take the charge off the capacitor and be able to use that energy for some kind of process that you want to have happen.